Last class. Before I start reviewing the material, two things to remind you. The final exam itself is December 14th at 9 o'clock. It's 3 hours long for twice. It is 60 questions, so it's twice as long as a normal midterm. You have a huge amount of time, way too much. There's essentially, is there ever anybody here after 3 hours? I don't think so. There is way too much time because some of you will sit there turning right answers into wrong answers, having stayed around too long. So learn when to stop. It's, again, 60 questions, so I think of 30 of those questions as the third midterm, covering the material since the second midterm. And the remaining 30 questions comprehensive. I can take them from anywhere approximately. So, I mean, this is just guideline roughly. Any questions about exam issues? I will remind you that the course evaluation, I believe it's got a day or two left. If you haven't completed it, please complete it. The deal is I drop your lowest problem set score if you complete it. I get a list of who did it and who didn't do it. Okay, so that then, I'll try to review the semester. I know from experience I run out of time, and so I give short shrift to the things that I put at the end. So I actually want to start with what I just was doing so that I don't leave it, and that is the musical instruments. You had to deal with these to a large extent on the problem set that was just due. Just to remind, the musical instruments, the vast majority of them behave as harmonic oscillators, but not just a single harmonic oscillator. They can actually behave as multiple harmonic oscillators in one string or one column of air. It has a bunch of ways, what are called modes, in which it can vibrate as harmonic oscillators. In each case, there is an inertial component and there is a restoring force component. And in the case of a string, it's pretty clear what the inertial part is. It's the string. It's got a mass. And the restoring force part is the tension in the string and the length of the string. They both contribute to how stiff that string is. That is, how hard it is to take that string 1 centimeter away from center. How much force it exerts back on you, restoring force. The tauter the string is, that is, the more tension it has in it, the harder it is to pull it away from center, 1 centimeter. So that stiffens the spring. It stiffens the restoring force if you tighten up the string, make it tauter. Also, if you make it longer, let's make it shorter. If you make the string shorter, it fights harder against you taking it 1 centimeter away from straight. It cares more. If it's a mile long, it barely cares at all. So the restoring force gets stiffer when you tighten the string and when you shorten the string. They both do that. Shortening the string also has the effect of reducing its mass, so it's a double. You get a double hit for it. Shortening the string reduces the inertia, which speeds up the rhythm, and stiffens the restoring force, which speeds up the rhythm. Any questions then about the basic idea with strings? Okay, and of course they can vibrate as 1 full string, that's the fundamental mode. 2 half strings, that's what's called the second harmonic mode. 3 1/3 strings and so on. How about air columns? A little more, how things break. Air columns are a little more mysterious. You know, what's the restoring force and what's the inertial part? The inertial part is the air. Air actually, of course, has mass and therefore inertia. And so, not surprisingly, the longer the column gets, the more mass it's got. That by itself is going to slow down the rhythm. But what is the restoring force part, and how stiff is it? The restoring force comes about when you have a wind instrument there. It's usually a column of air protected from the outside by a shell, a pipe, that isn't really involved in the vibration, but rather protects the air column from the surrounding air and its air pressure. So that you can do things like take the center of that air column and increase its pressure above atmospheric or below atmospheric. If it weren't protected by the pipe, that would lead to immediate movement of air to try to squelch its excursion away from atmospheric. So you need the pipe to protect the air column, but it's not part of the vibration. So whether you've got a flute that's made of silver, or a flute that's made of gold, or just a flute that's made out of plastic, it's going to have pretty much the same behavior. It won't sell as well, or probably won't look as good. It probably sounds better when it's made out of these fancy metals, but okay. The stiffness of the restoring force, where's that? If you take the air at the center of a pipe away from atmospheric by 1 unit of pressure, I don't know, above or below, the air doesn't like this. It's going to want to fill in or unfill that spot and bring it back to atmospheric. So there's a battle. The air at the ends of the pipe is at atmospheric. It's going to want to fix that mistake. And if the pipe is very short, it's going to want to fix that pipe. It's going to fix the mistake aggressively, because you're taking the middle away from atmospheric, only an inch or two away from where it is atmospheric. The air is really going to fix this fast. So that's a stiff restoring force. On the other hand, if the pipe is a mile long and you take the center 1 unit away from atmospheric, how does it even figure out that you've done this? It will be very slow. So the stiffness of an air column has a lot to do with its length, and that'll do it. Yeah, Liam. Does the diameter of the air column have anything to do with it? Approximately no, because it's approximately a one-dimensional movement along the length. That's not entirely true. The diameter does have some effect. It's not quite perfectly one-dimensional thing. And some instruments are not uniform along their length. They're bored not with they're not constant disc slice. They're conical, for example, or they flare out as the bell of a trumpet or a tuba. That changes the shape of the air column vibrating and its behavior somewhat. Other questions? So the main points, and I should just say the air columns can vibrate as multiple, as pieces they have harmonics also. For the ones that have strange shapes that are not conical and stuff, I'm not sure that they're exactly what are known as harmonics. I did not talk about the concept of an overtone. The modes that I described for the string are what are known as the harmonics. They're very simple, and they are integer multiples of the fundamental in terms of frequency. The frequency of the harmonics are integer multiples of the frequency of the fundamental, the most basic mode. For some instruments, that is not the case. That is, it has complicated modes other than the fundamental, but those modes have frequencies that are not integer multiples of the frequency of the fundamental. They're called more generally overtones, and they can sound kind of different. And I'm not going to pursue this today because it's a review session, but some instruments have a more complex variety of other sounds apart from the main note that you're playing. And we hear that, and we know, you can tell that some of these instruments, they have a more complex sound to them. All right, that's the basic story I wanted to tell you about musical instruments. I'll now rewind. Last questions about musical instruments? I'll rewind to the beginning of the semester and try not to spend much time on laws of motion because we've sort of built them into everything. But I'll remind you a few main points. And that the first and most important one is that forces don't cause velocity, they cause acceleration. So that, just to remind you what that means, it means that when you don't have to push on something for it to be moving. You have to push on it to change its motion, but the motion that it has, and I'm being a little simplistic here, is something that it had before you got involved. If it was moving, it will continue moving naturally without your intervention. If it was stopped, it will remain stopped without your intervention. The only reason why we don't see this all the time is because of things like friction and air resistance that kind of gum it up. They tend to take things that were moving and stop them anyway, even without you. But it's not that that you need to push something to make it move. It's you need to not push something to let it continue moving. That's the basic theme of the concept of inertia, really. And I introduced that with just these laws of motion. But the real underlying physics in this is the conservation law of momentum. If something's got momentum, whatever its momentum is, it's going to keep that momentum unless something exchanges momentum with it. So something at rest, a little wagon. A wagon that's at rest is going to stay at rest. Why? Because it has no momentum to start with, and until something gives it momentum, it can't start. It's forbidden. If it is moving, it will continue moving in a straight line at a steady pace because that's the only way it can carry its constant momentum with it. Until something is willing to exchange momentum with it, and that could be friction or air resistance or you, it's going to keep moving in a straight line at a steady pace. That's what an object with a constant momentum does. All right? The tablecloth trick, way back, I talked about it as being the source of inertia, that it being a demonstration of inertia. It is really more deeply a demonstration of the conservation of momentum. The stuff on the tablecloth had no momentum to start with, and I did my best to transfer as little momentum as possible to them in pulling the tablecloth out. How do you do that? Use a slick tablecloth that barely pushes, but it still pushes a little by way of sliding friction. But keep the time short, because remember, the mechanism for transferring momentum is an impulse, force times time. I couldn't get rid of the force, but I could make the time as short as possible. Okay? So that was for linear motion, translational motion. For rotational motion, same story. Objects tend to continue rotating until you transfer momentum, angular momentum, into or out of them. They have a little more complexity to them because objects can change their rotational mass. They can't change their mass, but by changing shape, they can change their rotational mass, and that allows them to change how fast they're rotating without changing their angular momentum. This is the skater trick stuff. Hopefully that's, you at least know where to look for those ideas. All right, anything else I want to say with the laws of motion? Yeah, forces cause acceleration, and you know how to sort of predict how much acceleration. It's simply the force divided by the mass. That will be the acceleration that the object experiences, assuming there are no other forces, which is to say that the force we're talking about is the net force, the total force acting on the object. There's a similar story for rotation. I talked about how to transfer, I talked about energy, and this just keeps reappearing throughout the semester. Energy was a big deal. Unlike momentum and angular momentum, which have a direction, energy has no direction. It's just an amount. But it really governs a lot of behavior and activity. It's the conserved quantity of doing things, and you give it to something. We saw the mechanical way to give it to something. You do work on it. You exert a force on it, and it has to move a distance in the direction of your force. So there are things like, questions like, when do you want to push a kid on a swing or a pendulum? A kid on a swing to make them swing harder and harder. Well, you want to push them as they're going away from you because you want to do work on them and give them energy. That's what makes the swinging motion bigger. More energy. So you push them as they go away from you when you can do work on them. So that's, we encounter work all over the place. There turned out later in the semester to be a second way to transfer energy to something, the thermal way, with heat. Heat also transfers energy. It's not, it's still energy. It's exactly energy, but it's not as useful as the energy associated with work. Work you really can do things with directly. Heat, it's harder to do things with directly, although not impossible. That'll do it for laws of motion. I mean, that's sort of the high points, I think. Yeah, Liam?
I remember you mentioned with the wagon, so if you're pulling a wagon uphill at a constant velocity,
yep.
Are you doing work on it, or is it just coasting up?
Okay, Liam's question is, if you pull a wagon, it's moving up the hill. You're pulling the wagon, it's moving up at constant velocity. The story all actually turns out to be completely self-consistent. The net force on the wagon is zero. So it is an inertial object. It is coasting. But that doesn't mean you're not doing work on it. You're pulling on the wagon handle. If you weren't, the only forces it would be experiencing are gravity down, support force up at an angle. It would accelerate downhill. So you have to pull up to allow it to move at constant velocity. And the fact that you're pulling and it's moving in the direction of your pull, that's all that matters in terms of doing work. You are doing work. You can just look through a cardboard tube at your hand. Oh, your hand's pulling on the wagon. It's touching the wagon handle and pulling. Job one, you got the force. And the wagon handle's moving in the direction of your pull. You're doing work. The rest of the story doesn't matter. You know, where's your work going? It's going into gravitational potential energy in the wagon. It's storing it, not disappearing from the universe. So, yeah. Other questions? Okay, so next time, what was the next topic? Before about spring scales. Yes, so spring scales. I talked about yet another sort of source of force, and that is objects that are bent out of shape, like a spring. And you can picture the coil spring, but there are lots of different shapes of springs. If you bend them out of shape, they develop restoring forces that act to push them back to their original shape. They have an equilibrium shape, and they want to go back. And for real springs and for an awful lot of other objects in life, those restoring forces are proportional to how far you take them away from equilibrium. And they're therefore really good for making harmonic oscillators, right? We see that later on. I had you guys bouncing up and down on a bungee cord, and to an extent a bungee cord is like a spring and it's got the right restoring force. You are bouncing up and down on that bungee cord as a harmonic oscillator. They just come up, harmonic oscillators show up everywhere to a very good approximation. The value of a spring in the context of a spring scale is that you can weigh things. That is, you can determine their weight. And it's a little bit circuitous how you figure out their weight. You support them using a spring. So you use the force from a spring to balance away, cancel the object's, the melon's weight. And you notice that the melon is not accelerating. That's key. You have to make sure that you're really balancing the weight. And if you really are, the melon won't accelerate. If it's accelerating, all bets are off. So the melon's supported properly by the spring, not accelerating. How hard is the spring pushing? Because if you know how hard the spring is pushing up, that's equal in amount to the weight of the melon down. So how do you figure that out? Look at how far the spring has been distorted. How far has it been bent away from equilibrium? It's a spring. It obeys this thing called Hooke's law, which is that the force it exerts on its ends are proportional to how distorted it is. And if you look up in the specification for the spring how much force it exerts for a given distortion, you measure the distortion, you can calculate how hard it's pushing. In fact, you calibrate the spring. You know the relationship between its distortion and how hard it pushes. And you're done. So that's what spring scales do. They use the distortion of the spring to determine the weight of an object in that approach. If the melon's accelerating, don't count on the spring's distortion having much to do with its weight. So if you jump up and down on a spring scale, it's reading all kinds of crazy things because you are accelerating. All right? That'll do it. Questions about spring scales and stuff? Springs? Bouncing balls. Not exactly springs, but they have a lot of same characteristics. Not exactly springs for the reason that restoring forces aren't proportional to distortion. They're messy. They're three-dimensional, weird objects. But they do nice things like they bounce or not. And during the act of bouncing, there's a whole process involved of the surface denting inward and storing energy and then undenting and releasing that energy. And some of the energy comes back and some of it gets lost due to internal messy stuff inside the ball. So it bounces well or bounces badly. And the bounce is easiest to think about when it bounces off a completely rigid hard surface, cement floor. Then the ball does all the denting, does all the energy storage or not, and returns that energy, and it leaps back up to some good fraction of its original height if the ball is good at storing and returning energy, or it just goes plop if it's terrible at storing and returning energy, like a beanbag. The ball, I've asked you thousands of questions over the time about what conserved quantities is the ball able to convey to the floor, and which one's not. It has a terrible time giving energy to the floor because it can't do work on the floor because the floor won't move. But it can convey momentum to the floor. And a really lively ball, because conveying momentum, you have to exert a force for time. Time's not a problem, so you don't have to worry about anything moving. You just transfer momentum to it. A bouncy ball actually transfers more downward momentum than it had to the floor, and consequently ends up with a deficit of downward momentum, which is upward momentum. So its ability to leap off the floor involves a transfer of momentum that's bigger than it even had to start with. All right. I talked about momentum transfers being slow or fast. The slow ones, because there's a lot of time involved, the forces typically are small. On the other hand, a momentum transfer that's fast, because there's not much time involved, often involves a big force. So my quip, once again, is that we go through life trying to avoid fast, sudden transfers of momentum, because they hurt, because they involve big forces for little times. All right? Bouncy balls. All right. Next topic after bouncy balls was roller coasters and carousels. This was the story of the experience of accelerating. So up until this point, we sort of I talked a lot about accelerating, but we weren't so much the thing that was doing it. And if we are the thing that's accelerating, we notice this. I told you about how we notice gravity itself, the existence of our own personal weight. We notice that because, one way to see that you've got a weight is to jump off jump off a building. Bad idea, okay? You will accelerate, and we know, okay. So alternatively, you just can stand there and have the floor support your weight at your feet, and then you will experience all these stresses within your body as the different parts of you try to support the parts above them. And this is what you feel. You're feeling right now. You're feeling your weight as those stresses. You basically have a choice. If you jump off something, you don't feel your weight, and you are quite aware of the fact that you have weight because you are accelerating downward as a falling object. On the other hand, when you're standing here, you're not accelerating down, which is a good thing for the most part, and you're, however, experiencing all those stresses. When you accelerate, you feel the same stresses. They're not there to support your weight anymore. They are there to accelerate the parts of you, so that all of you accelerates in the direction that whatever the situation had in mind. So if you accelerate to the right because the chair, the back of your car seat is pushing on you to make you do that, you feel all these stresses through you as the various parts of you are trying not to accelerate and are having to be shoved forward by all the parts behind those parts. So you experience stresses again, and they're indistinguishable from the stresses associated with actual weight. So I call them the feeling of acceleration. What's the difference? It turns out fundamentally there's very little difference. That's a whole story of general relativity. But with the experience of real weight, it's very specific. You have a very specific weight. It depends a little bit on where you are on the surface of the earth because gravity is a little bit dependent on where you are. But otherwise, it's pretty fixed. You have nothing you can do to play with it. The feeling of acceleration, however, depends entirely on how strong and what direction you're accelerating. It is in the direction opposite your actual acceleration, and it's got a strength that's proportional to your acceleration. So if you're accelerating at 9.8 meters per second squared, you will experience a feeling of acceleration that's exactly the same strength as your feeling of weight. But it'll be in the direction of your acceleration. So, to the right, to the left, up, down, it's all flexible. And if you happen to be accelerating downward at 9.8 meters per second squared, your feeling of acceleration will be upward and exactly as strong as your feeling of weight, and the two will cancel. So you feel nothing. You feel, in quotes, weightless. You're genuinely not weightless. You have every bit as much weight as you always did. It's just that you can't feel it. Okay? It's as though you went and did, well, you can't feel it. I call the sum of those two feelings, your feeling of genuine weight and your feeling of acceleration, together they're your apparent weight. It's what you only feel one thing overall, and it's the sum of those two, taking into account their direction, and I call that apparent weight. And your apparent weight when you're falling is 0. Your apparent weight when you're accelerating upward like crazy in a rocket or in an elevator that's just started up on its way to the 800th floor of the newest, biggest, tallest building ever. Because you're accelerating upward, you experience a feeling of acceleration downward, which adds to your actual feeling of weight. You feel a tremendous apparent weight downward. You feel super heavy. All right? Any questions about these sort of basic mechanical-y things? Like, okay. Bicycles, mostly the story, the dust settled, mostly the story of various types of equilibria, stable and unstable. Remember, stable equilibria are ones where if you, first of all, they're in equilibrium. You're in a situation where you're experiencing zero net force. That's equilibrium. And it's stable because if you make an excursion away from it in any particular direction or tilt, forces or torques show up that push you back, that try to get you back to that equilibrium. And those, a stable equilibrium is usually, well, usually it's always, a situation where when you leave equilibrium, your total potential energy goes up. And you return to satisfy a simple version of a simple law that's associated with forces and potential energies. And that law is that you accelerate in the direction that reduces your total potential energy as quickly as possible. So if you're in a stable equilibrium and you leave that equilibrium a little bit, your total potential energy goes up, and you accelerate back toward equilibrium to reduce your total potential energy as quickly as possible. If it's a chair being tilted or a tricycle being tilted, your total potential energy that's going up is your gravitational potential energy. There's nothing much else around. And it happens because your center of gravity goes up and you're storing energy in gravity and you want to go back. Reduce your total potential energy. But any other potential energy will work just as well. So magnetic potential energy or nuclear, I mean, all right. Tricycles have a nice, stable equilibrium. Bicycles don't. They have an unstable equilibrium. When you're exactly over the wheels on a bicycle, you're in equilibrium, but it's unstable. If you leave it, forces and or torques show up that take you away from equilibrium, not toward it. And that's associated with being at a maximum of total potential energy. It's a little more complicated than that, but basically, you're in a situation where if you tilt in at least or move in certain directions, all it takes is one, and your total potential energy begins to decrease, well, you'll go that way because you will accelerate in that direction. So once you begin to tip on a bicycle, it's a catastrophe. You keep going over and over, plop. The bicycle turned out to have it was rescued by dynamics of its forward motion. When a tricycle's moving forward, it's still got a stable equilibrium, but it's got things that can happen that make that stable equilibrium irrelevant. If you make a really fast turn on a tricycle, your top part is going to go inertial. The bottom part will drive out from under you. The fact that the tricycle has a stable equilibrium and forces will begin to appear trying to get you back to it. Yeah, that's true. The tricycle will try to rescue you, but if you're doing it fast enough, its stable equilibrium stuff just isn't strong enough. You crash anyway. Your inertia just wins. So a tricycle's not very stable in motion, or it's got issues in motion, and that's true of cars too. You can flip cars because they have exactly the same problem tricycles have. They can go, the body goes inertial, the car drives out from underneath itself. Bicycle it is unstable at rest, but once it's in motion, it can perpetually rescue itself by driving under its own center of gravity. And it does this spontaneously for two reasons that have to do with the steering axis and the rotation, the angular momentum in the front wheel. That those two together manage to keep on causing it to drive underneath you and rescue you, so that although you are truly in an unstable equilibrium, when you're moving, you could stay up almost effortlessly. Rockets. Any questions about bicycles before I leave it in the dust? All right, rockets. Rockets came out of mostly a very simple observation that if you throw something to the left, the act of pushing it to the left causes it to push you to the right. I mean, that's not very new. That was Newton's third law, action-reaction. And in this case, you push it to the left, it pushes you to the right. You can accelerate to the right without having pushed on anything outside the pair of you and the thing you threw. That's all it took. You could be in deep space with a box of tennis balls and a racket and just keep whacking them off that direction. And every time you do that, whack, off it goes. It will push on you and the tennis racket, and you'll accelerate toward the right. So then that leaves rocket propulsion just down to the details of how do you make the stuff heading off to the left go as fast as possible so that it makes you go as fast as possible in the other direction. And the details involve things like, well, I should say before I get to the details, there's just the issue of momentum. I mean, the sophisticated way to look at this arrangement, you push on it, it pushes on you, is in terms of momentum. That the act of smacking those tennis balls off toward the left involves giving them leftward momentum, which is taken out of you. So you begin to run a deficit of leftward momentum, having given it away to all these tennis balls. And the deficit of leftward momentum is rightward momentum. So you begin to accumulate rightward momentum for having given away leftward momentum to the balls, and off you go. The details are things like it becomes progressively harder to go faster and faster because you need to keep throwing this stuff out the back, the exhaust. You're limited by things like how much mass you have to throw out the back, how fast you can throw it, which is to say how much momentum you can give to each kilogram you throw out the back, and to the sad fact that early in the process of propelling yourself, you invested some forward momentum in material you will subsequently throw out backwards. And the fact that you've already given it some forward momentum and you just can't salvage that back means that you just can't concentrate all of the forward momentum in the last little bit, the spacecraft. You actually waste some of it, giving some of it to the fuel that you'll eventually throw away. So rockets there's sort of an inefficiency that gets worse and worse as the rocket goes faster and faster. Nonetheless, you can get the rocket going awfully fast, much faster than its own exhaust velocity, which is key because, for example, to go into orbit, and now turn to that sort of issue, taking a rocket straight up and straight down, not so hard. People have been doing this for, well, probably since the 40s for sure. Up and down, not a problem. It will be the early space tourism will be the up and down. But the rocket reaches peak height, it's motionless, it just becomes a falling object and it falls, it works its way back down to the dirt. It's a brief, perhaps very exciting, probably hair-raising experience, but not very long. If you go up and tilt sideways and go very fast sideways, which is to say aim towards going to orbit, something special shows up. You get to going so fast horizontally that even though you run out of fuel not motionless, but rather moving sideways very fast. It's very different. You don't just simply fall back to the earth. You run out of fuel while coasting sideways. Well, not coasting because you're still experiencing gravity. You begin to accelerate. You're in free fall. You're going sideways. You're in free fall, and that by itself sure sounds bad, like you're going to be back in the dirt very soon. However, if you're going sideways fast enough, as you accelerate towards the Earth's center, the Earth curves away out from under you, and you don't make any progress towards the Earth's surface. Yeah, you're accelerating and picking up speed towards the center of the Earth. However, you're going sideways, and the Earth keeps turning away from you. arcing out from under you, and you maintain constant altitude, or approximately constant altitude. And that's what orbit is. It's free fall, but it's free fall with such a huge sideways component of velocity that the object never makes much progress towards the surface. Maybe a little bit, but then it'll be compensated later on by making a little progress away from the surface. The orbits are either circular or they're elliptical. I mean, the details don't matter very much, but they all involve making no average progress towards the Earth's surface. And that's all of the satellites and human-occupied spacecraft. They're all doing that. They're all in free fall, making relatively little progress one way or the other towards the Earth's surface as it arcs away out from under them. Any questions about rocket stuff? I think that's pretty good justice to it. That brought us then to all this stuff about fluids. Balloons, remember balloons. The Earth's atmosphere, being a gas, supports its own weight. It's got thermal energy, so gas molecules are moving like crazy and they're bouncing off each other and they develop pressure as a result. Pressure being a fluid's way of pushing on things. Force per surface area. And the Earth's atmosphere has pressure in it, and one of the cause of that pressure is its own need to support the weight of the air above it. If there were no pressure, the air would all collapse onto the Earth's surface due to its weight, and it would just be a puddle. But that's not the case. It's pushed up by pressure down here, and the pressure down here is greater than the pressure up at the ceiling of the room or above the building or up in the clouds, because the higher you go in this sort of stack of gas, the less weight there is overhead, the less pressure you need to support it, and the air expands and thins out just right to develop only the pressure it needs, no more, no less, to support the weight of that air. So we've got this pressure gradient in the Earth's atmosphere caused by gravity. And if you start sticking stuff into the air, replacing air with something else, the surrounding air doesn't notice that you've changed anything, and it keeps doing its best to support the blob of air that used to be there. I mean, the air right here is supported by the higher pressure down here pushing up on it. That's part of the stack over this air, is this ball of air I'm holding in my hands. If I take the ball of air out and put a balloon in there, or put a big blob of lead in there, or I put whatever you like in there, the air around it is still going to push up on it, the same as always. And that creates what's called the buoyant force. And the buoyant force, as observed in Archimedes' principle, is exactly equal to the weight of the air you took out to make room for this object. And even if it's not just pure air, if it's air and solid oil and water, whatever the mixture was of stuff that was being supported by the surrounding mixture of stuff, when you take it out and replace it with a log or whatever, the force on it's still going to be the weight of the mixture of fluids you took out of the way. So that allowed us to support balloons. Not any old balloon. The balloon had to weigh less than the fluid that it displaced. So the balloon had to be made of really light stuff. For example, hot air. Hot air is lighter than cold air. Why? I should say per liter, per unit of volume. Why? Because the air molecules with more thermal energy are more able to create pressure, each one. They do a better, each air molecule does a better job of creating pressure. You don't need as many. So you can lessen the density of the air when it's hot and still get atmospheric pressure. So a hot air balloon has fewer air molecules in it than it would if it were full of cold air. It just doesn't need as many to fill this space with atmospheric pressure gas. So it weighs less than the air is displaced, and up it goes. Alternatively, you can replace the air molecules with helium atoms. Helium atoms, despite being very low mass, very light, do just as good a job of creating pressure as the air molecules. And so you take out a bazillion and 7 air molecules and you put in a bazillion and 7 helium atoms, you're back at atmospheric pressure. And yet it weighs very little. And so it's much lighter than the air it displaces. The buoyant force is greater than its weight, and up it goes. All right, questions about balloonies? All right. water distribution. We saw that if you take fluids, now it became just not just gases, but gases and liquids, they all together are fluids, and you can mix and stir them, and they're not identical, but they follow a lot of the same rules. And if you start sending one of these fluids, it was water for my stories, through pipes, you start to notice that they have a couple forms of energy, and they can exchange the energy from one form to the other and carry it with them in this mixture, this dynamically changing mixture of forms. And the three forms that mattered, they're ordered forms of energy. That is energy that's equivalent to work, that can actually do work directly, as opposed to what? As opposed to thermal energy, which can't. So the three ordered forms of energy were gravitational potential energy in water that's up high, kinetic energy in water that's moving fast, and pressure potential energy in water that's at high pressure. And if you follow water flowing through a stationary plumbing system, and you stick with one streamline in principle, that you have to follow the water that all had the same history, that followed the same path. As you watch that water go through the system, it can exchange its energy between these three forms. Gravitational can become kinetic can become pressure, and the whole mishmash. And that allows us to sort of follow things like water coming out of a water tower, descending, becoming high pressure water, going through the plumbing, going into your house, going to the shower, becoming kinetic energy in the shower head, spraying like crazy, hitting you, pushing hard on you as its kinetic energy becomes pressure potential energy. It's all in there. In the next story, the garden watering, I started pointing out that, well, that's all well and good. It sounds great, but there are some details here that we swept under the rug. For example, viscosity. Water doesn't flow perfectly. It fights against, when portions of water move relative to one another, they fight each other. And so really, water does tend to waste some of those three ordered energies. It tends to waste them and turn them into thermal energy, sort of given certain situations. For example, if you let water flow too easily and too fast through plumbing, it rubs too much, wastes a lot of its energy as thermal energy, and it comes out of the end of a hose with not much kinetic energy, not much gravitational potential energy, and no pressure potential energy to speak of. It's coming out at atmospheric pressure. Where'd the energy go? It became thermal energy. So viscosity was important there. Water can also not flow perfectly and begin to tumble and swirl, and that was a different kind of flow than we'd encountered before. Turbulent flow. Turbulence involves this chaotic motion within the fluid that again chews up its energy into thermal energy. It also makes it hard to predict where the water's going to go. It loses its simple mechanical flow and becomes kind of a fuzzy mess. And that started to become important. I'll go on to looking at aerodynamics. So I switch back to air, and then we watch air flow around balls. And as it does that, for one thing, it develops turbulence, and that leads in several steps, which I won't rehash. It leads to a type of air resistance known as pressure drag. If the air flowing around a ball starts tumbling after the ball, there's a high pressure in front of the ball that's never balanced, that is unbalanced by anything behind the ball. And so there's a backward push on the ball, and it's pushed downstream by the air. I should point out that the origin of the high pressure in front of the ball has to do with bends. That the air encountering the front of that ball has to bend away from its surface so as not to go through the ball. And that bending away from the surface involves a pressure gradient. The pressure's got to be different at the surface than it is far from the surface. And the pressure, because the air is bending away from the ball, it's pushed away by high pressure at the surface of the ball. So that's the high pressure at the front of a ball. On the sides of the ball, the air is bending still. It's bending now toward the surface of the ball to wrap around it. And so there's low pressure at the surface of the ball, allowing the surrounding atmospheric air to push in and bend this, to wrap this airflow around the ball. The back of the ball, you get these turbulent wakes, and that leads to the pressure drag. It's good enough for balls. Last thing with fluids was airplanes. And airplanes take advantage of these bending effects in the airflow and the related changes in pressure to support the weight of a plane. So as air goes around a plane's wings, it bends away from the bottom of the wing, and this is partly because of the shape of the wing and partly because of the tilt of the wing, what's called the angle of attack. The air bends away from that bottom surface of the wing, and how do you make air bend away? Push it. So the pressure at the bottom of the wing is high. It's greater than atmospheric. And the air going over the top of the wing bends toward the wing. How do you get the air to bend toward the wing? Don't push it. So the pressure at the top of the wing is less than atmospheric. So there's a big pressure imbalance across the wing. It's pushed upward by the air. And you can think of that in terms of these airflow effects and the wacky pressures that result. Or you can think just pure Newtonian view, which is that the air in going around the airplane wing is deflected downward. It came along, minding its own business, traveling horizontally, and after the wing goes by, the air has been pushed down. It's going down. And if you bend the air down, it's going to push up on you. And so that's what happens with the plane's wing. It's pushed up by the act of bending the air down. All right. The story of heat and moving heat. We saw that if you got a hot object and a cold object, heat flows naturally from hot to cold. Initially, that was just, I just told you did it. And subsequently, we saw that it happens because flow of heat from hot to cold increases the entropy of the system or the universe and is therefore statistically likely. Heat flows from hot to cold for statistical reasons. And it flows, the three mechanisms are conduction, convection, and radiation. Conduction and convection, pretty straightforward, I hope, something you've sort of encountered before. Radiation, a bit more mysterious. This is the fact that objects can emit their own thermal radiation associated with their own temperature. And bizarrely enough, objects that are black, which is to say objects that absorb all the light that hits them, are also the most effective at emitting their own thermal radiation. The fact that they're black, that they absorb all light that hits them, tells you something about their ability to interact with light and light's relatives, and says that they're very good at it. And they're very good at absorbing light. They're consequently very good at emitting it. So black objects glow as brightly as possible given their temperature. In contrast, things that are shiny or white or transparent don't do a good job of interacting with light and light's relatives, and therefore they don't emit thermal radiation well at all. They often will reflect back somebody else's thermal radiation. Water, steam, and ice. I told you about the three phases of water. You know these to some extent well. I will remind you that the mist over a tea kettle is water droplets. It's not steam. The steam is a clear gas that comes out of the nozzle before it has had a chance to cool in the room air and form the droplets. So steam is an invisible gas. When you have these three phases around simultaneously, they are exchanging molecules all the time. And a lot of the issues of the phase transitions, of one turning into the other, water turning into gas or gas turning into ice, whatever, have to do with the landing-leaving process. If landing outnumbers leaving, you accumulate the liquid or the solid. If leaving outnumbers the landing, then you accumulate gas. That was used later in air conditioners. I'll finish up talking about air conditioners and automobiles. These are devices that use the movement of heat, that manipulate the movement of heat very strategically. In an air conditioner, it uses work to move heat from place A to place B against its natural direction of flow. That is, it moves heat from a cold object to a hot object. And that, yes, that doesn't happen naturally. That by itself would create order and therefore reduce entropy, and it's a no-no. So the act of pumping it involves chewing up order from somewhere else, typically purchased from the electric company, to move heat the wrong way. The production of additional entropy makes up the deficit so that the net entropy of the world does not decrease. And so air conditioners can pull this off. Automobiles do the reverse. They let heat flow the way it likes to flow, from hot to cold, but they divert some of it. Under the law of entropy, they can do that, and they turn it into useful work. And harmonic oscillators I already talked about at the beginning of the hour, so I'll call it a day, and I'll see you guys December 14th. Thanks.